Yeah, so a little bit of a different topic than what you've heard, but in line with what will we do when we have things that are in lunar applications or asteroid exploration applications that are going to be exposed to all of these fine dust particles that we've seen are being so well characterized by a lot of survey programs. So as we know, lunar dust exposure can cause contamination, abrasion, and static charge buildup on surfaces that we're going to use for lunar exploration. In particular, we're worried about the abrasive, insulating, and size aspects of these particles. So in the lower left-hand images, you can see an example of particles returned from the Apollo missions. And then in the right-hand images, you can see the abrasive wear that occurred on Apollo suits during the very short durations of EVAs, which are obviously much shorter than what we expect during Artemis missions. So as we move forward and we put materials like polymeric materials that are going to be on the exterior applications, we need to think about how to protect those surfaces. So one way to protect them is to impart electrical conductivity to the surface for both passive protection, so that would be like static charge dissipation, as well as active protection through devices that we'll discuss later in this talk. So our approach to doing this is using a reduced graphene oxide chemically modified particle. So the concept here is that we have a conductive nanoparticle that we have grafted short polymeric chains to enhance dispersibility and miscibility with polymer matrices, which allows us to perform this processing. We take these particles, suspend them in an organic solvent. We typically use chloroform, although they're dispersible in a number of solvents. We use a commercial airbrush to spray them onto the surface. So this makes a fairly thick, disordered, very porous nanocomposite coating. We then take this entire assembly and we apply a static pressure and heat, and this allows the polymer substrate to actually infiltrate that sprayed coating to make a surface localized electrically conductive nanocomposite structure at a much higher loading than we would be able to get from a melt blending type approach. And so what you can see in the center image is what happens if we process these at a low temperature. So for polymers, low processing temperature means high viscosities. So we expect to not get a lot of infiltration. And what you can see in the cross-sectional SEM image is that we do in fact have a polymer substrate and then a primarily uninfiltrated nanoparticle coating. As we increase the processing temperature, we get better polymer infiltration. And we actually get a very robust defect-free nanocomposite coating that is well adhered to the polymer substrate, in that it is the same set of sort of entangled polymer chains. So that's really an encouraging result. So in terms of what do we do with these things, as I said at the head of this presentation, we are interested in exterior materials for lunar exploration applications. So in collaboration with Dr. Micah Shapel, we looked at exposing these things to the LMS1 simulant that Ashley talked about at the start of this session. They're also under high vacuum, as well as applying vibration and some UV exposure. So if we look at a composite that's processed at a middle processing temperature, so this is a partially infiltrated composite, on the far left is the unexposed. So you can see there's a lot of surface variation. That sort of indicates that there's roughness and porosity where we think that grains could be trapped and abrasion could occur. We do have fairly good surface resistivity. This is orders of magnitude more than what we need for static charge dissipation at 68 ohms per square. When we expose these things to the lunar simulant condition, we do see that the surface resistivity goes up a little bit. That's sort of as expected as we get simulants stuck and sort of working its way down into these porous surfaces. And we maybe see a little bit of abrasion, which you can kind of make out in the lower right-hand corner of the middle image, where we've got a bit of texture variation in the optical image. So those surfaces are probably not the right choice, but if we progress to that higher processing temperature, so you remember that this is a fully infiltrated composite structure now, you can see in the optical image on the left that is a very smooth surface that looks to be relatively defect-free. And then when we expose it to simulant, we see very little, this is a statistically insignificant change in the surface resistivity and less dust adhesion after exposure. So this is an encouraging result. But like I said, these surface resistivities are orders of magnitude more than what we would need just for static charge dissipation. So we took this and we looked at an active device configuration. So we chose an electrodynamic dust shield as the device configuration. Electrodynamic dust shields, for those of you who are not aware, I assume that's probably no one in this audience, are multi-phase interdigitated electrodes that we apply a variable waveform to make a traveling electric wave that lifts and moves dust off of, or not just dust, any sort of charged particles off of the surface. Typically, these are made with rigid materials like ITO and copper put onto rigid substrates. So for things like solar panels, that's a great application. You can use a transparent conductor like ITO, and you can clear the dust off of solar panels, which is the application shown in the top right images. As we move towards flexible structures for long duration exposure, so think things like inflatable habitats or spacesuits that are going to be used over a lot of EVAs, we need to start thinking about how we integrate these technologies into those flexible substrates. So there's one really great example already published in the literature where they used carbon nanotube threads woven into spacesuit materials as interdigitated electrodes. And you can see in the bottom images that it was effective at clearing dust from the surfaces. So that's very encouraging. So how do we do this with our substrates? We took an approach that is just a very simple masking approach. So it's the exact same process, except in the spray process, we insert a removable mask. So in the bottom images, you'll see before deposition, just a mask clipped to the substrate. And then we spray over the mask, we remove it, and then we follow the same processing steps to basically make nanocomposite wires that are integrated into the polymer substrates. And then again, in collaboration with Dr. Mike Schabel and our collaborator, Chris Solden, we looked at how these devices clear dust from the substrates. So you can see after dust deposition, we've got a pretty good coverage on the device. And then as we apply a low voltage, we get fairly good dust clearance. And then as we increase the voltage, we get additionally better dust clearance. So this was really encouraging because these are as produced devices. So no additional processing needed. But what we wanted to look at is sort of how to get these things a little bit closer to the state of the art for what we know for traditionally manufactured EDS devices. So we've been working on some next steps that include the addition of a dielectric layer that will isolate the electrically conductive traces from the environment. So we've tried two approaches. The tape-based Kaptons is just single-sided Kapton tape stuck to the surface. And then we've also tried a full composite configuration in which we infiltrate the sprayed layer from both sides to make fully isolated and contained nanocomposite wires, which is sort of, we think, the first example of that sort of device configuration that's been produced. We're also looking at adding UV exposure to assist with dust clearance and a three-phase design, which is a little bit closer to the state of the art of what works in sort of rigid applications. So in summary, we've developed a robust, scalable approach to making conductive, physically robust, surface localized nanocomposite structures. We've characterized those nanocomposite structures fairly thoroughly beyond even what we've showed here in the presence of vacuum, mechanical vibration, and dust exposure. And then we've developed a polymer nanocomposite-based device and shown that it is effective in clearing dust. So I'd like to thank NASA Survey Reveals for my funding, as well as IEN and the Materials Innovation and Learning Laboratories at Georgia Tech for equipment access. And if you'd like to learn a little bit more about our more recent progress, that would be summarized in that next steps bit, please see Chris's poster at the poster session this afternoon.
Thanks. Any questions?
Hi, a very nice talk. So applied voltage 1 and 2, what was the magnitude that you were?
Yeah, so the first magnitude I think is about a kilovolt, and the second one is about 3 kilovolts. We have progressed since then. Those were sort of initial trials.
And so this is for astronauts or?
So yeah, we know that very high voltage, those sorts of very high voltages, we couldn't apply to the exterior of a spacesuit. So we're working on how to make these systems work at lower voltages, so that things like spacesuits could be a good application. Inflatables could be another place. There's sort of a challenge too that these are going to be, the traces will be black, because it's a graphene like nanoparticle. So sort of understanding to the integration with all of the other constraints on those exterior surfaces is something we're going to have to consider. But at this point, we are at the proof of concept, see if we can get it to work phase.
Thank you so much.
Yep.